So welcome back everybody. Here we go. We start again from where we stopped last time. We stopped at the quantization noise. Yes, everybody with me, everybody focusing, everybody remembers where we stopped last time, where we talked about the quantization noise. And we said the process with quantization produces a noise, and we call this noise quantization noise. And the way we calculate this noise is to subtract the actual message from the quantized value. Then the difference between these two values, we call it noise. And we need to quantify this noise and understand and study its effect on the received signal. So the use of quantization introduces an error between the input signal M, which is the message, and the output signal V, known as the quantization noise. The quantization error, therefore, is defined as Q, which is equal to the message minus the quantized value, V. V is like 0.01, 1.5, 2. It's a quantized, finite set number of values. So the value of a quantization noise will be bounded between minus delta over 2 plus delta over 2. And what's delta? It's the step size. And how do you calculate it? Delta, if I ask you to calculate delta, how do you calculate delta if I give you a waveform and give you the maximum and minimum and number of levels? How do you calculate it? Maximum minus minimum over number of level, you get delta, which is required to which you will need it in your calculation and in your quantization process. So this is we talked about. After this, since we need to quantify the quantization noise, we need to understand the probability distribution function of this noise. And how do we derive this noise, the PDF of this noise? Usually the quantizer input M is a sample value of zero mean random variable M. So we assume that the message is random, which is normal to assume because you never predict, you never know what type of information you are going to send. It's random. And this message, we assume its mean to be 0. The mean is 0. This means the quantization noise, which is a Q, and that's equal to M minus V, also a random variable which is going to have a mean of 0 because the message signal has mean of 0. Now we need to find an expression for the signal to quantization noise ratio. To find that expression, we need to find the PDF. PDF is the probability distribution function, and we defined it many times, and it's basically the histogram of something. The PDF tells us for each event, for each value, how many times this value is gonna occur. And accordingly, you will be able to calculate the probability that value will appear in your system. For example, let's say that you have 4 different values of quantization errors. Minus delta over 2, minus delta over 2 plus 1 over 4 delta, delta over 2, and delta over 2 minus 1 over 4 delta. You have 4 values. Then you start counting, for example, what's the probability that I will have delta over 2? How many times I'm gonna having this? How many times I'm gonna have plus delta over 2 or minus delta over 2 plus quarter delta minus quarter delta? Of course, since this is uniform quantization, all the possible values of the quantization noise are going to have the same probability. And if all the values are going to have the same probability, this means that we have uniform distribution. Then the PDF of the noise, of the quantization noise, is uniform, and uniform distribution is an easy distribution. You can find its mean, its variance, and derive it, integrate it, because at the end of the day, it's not function of any variable. It's constant, one value. So accordingly, now becomes easier for us to find the PDF. But before that, let's consider we have a message signal, input signal M, of continuous amplitude in the range minus M max, and the maximum amplitude is M max. The step size delta will be defined as delta equal M max minus M min. Since M max is equal to M min, then you end up having 2 M max over the number of levels, which is L. Then you will have delta equal to M peak to peak over L, which is simple. This is what I explained that just said in the previous slide. So what else now? Having understood what's the value of the delta and the meaning of L and max and min, now we just need to find the PDF of the quantization noise. If the number of quantization level is given to you, which is L, L can be 8, 16, 32, 65, 128, 556, 1024, any value, like of an order 2 to power. We can assume that the quantization error Q is uniformly distributed, and I explained to you why it's uniform. This means that the PDF of Q can be written as any Q value, any value of the quantization noise between minus delta over 2 and delta over 2, it's the probability to happen, how much? 1 over delta. Because if from minus delta over 2 till delta over 2, what's the distance? Delta means you have delta number of values. If you have delta number of values, and all of them they have the same probability, then what's the probability that any one of them will appear? 1 over delta. And that's why from 1 over delta is actually constant, and it's this the value of the PDF. Isn't it constant? It's constant because the variable is Q. It's the quantization value, but the probability is independent of Q. It's always whatever Q is, the probability is constant, 1 over delta. So the probability increases when delta, exactly when delta decreases, inversely proportional. So here we go. To find the signal to noise ratio, what do we need? Signal. Everybody with me? Everybody understands signal to noise ratio? The signal power divided by the noise power. What's the noise power? The noise power is the variance. How do we find the variance from probability? How do we find the variance? The variance here, the variance is equal to the expectation of the variable square, whatever that variable. Since we are dealing with noise now and we have a quantization noise, the variable is Q square. And how do you find that expectation? What's the expectation? Expectation means the mean. The mean of not x, the mean of x square. Here we have the mean of Q square is equal to, you put the variable Q square inside the integration and you multiply it with the probability distribution of the quantization noise, which is FQ of Q. Now, you just need to substitute the value of the PDF, which is equal to 1 over delta. What's this? FQQ. What's this? 1 over delta. Didn't we found it in the previous slide? 1 over delta. 1 over delta, since delta is constant, you take it outside of the integration. You are left with the integration of Q square. It's so easy. Integration of something square, just cube to 3 over 3. And after you substitute the values from minus delta over 2 till delta over 2, you get the integration of this Q square is equal to here Q cube over 3. And you substitute the value from minus delta over 2 over delta over 2. When you substitute these values and subtract them from each other, you will get this answer. What does this answer represent? This represents the variance of the quantization noise, which is equal to the power. Why it's equal to the power? Because the mean of this noise is 0. If the mean of any random variable is equal to 0, then the quantization, then the variance is actually the power. If the mean is not 0, the variance is not the power. Clear? The power will be the mean plus the variance. Everybody got this? You might be surprised that how variance is power, but this is how it is. We link random variables now, probability, with circuit theory and power of the signal and system. And we need this in the analysis of your modulation scheme, for example, MIMO antenna number modulation. When you find the signal to noise ratio, you need to find this. You need to find the probability of your transmit signal. What would be the BDF of your signal? The BDF changes according to your design changes. And once you find that probability, you need to find the variance, the power of that signal. How do you find the variance? By this method. And once you find that value, this becomes the power of your signal. You put it in the numerator. Here, since this is noise, the noise in the denominator, we will put this value in the denominator. Clear? Very, very profound concept. The relationship between variance and power. Recall, we know that delta is 2 M max over L. For binary representation, the number of levels can be written. If you want to interpret the number of levels in terms of binary representation, then we all know that the number of level is actually equal to 2 to power r, where r is the number of digits that you require to represent each level. Total number of bits for representing each level. By substituting the value of L and delta in sigma square, we get sigma square, the variance is equal to this. What did we do actually here? You remember with me here? Here we got delta square over 12. I just replaced delta by its value, which is equal to 2 M max over 2 to power r. Yes? And this is it. This is the value. I didn't do anything, just it's still, this is equal to delta square over 12. But what did I do? I just delta, what's the value of delta? I replaced delta by this. By the way, 2 to power 2r, what's it? 2 to power 2r. It's 2 to power 2 multiplied by 2 to power r. Is that clear? This is equal to 2 to power 2 multiplied by 2 to power r. And this is 2 to power 2 is equal to 4. 4 multiplied by 3, 12, which is that 12 that was in the first equation. Clear? This is another expression for the variance of the noise. Now, having calculated the variance of the noise, which is the variance of the noise is the power of the noise, which is in the denominator, and to find the value of the S and R, you just need to know the power of the message divided by the variance of the noise that we have just calculated, and then you end up finding the signal to noise ratio of your signal due to your quantization. So if the average power of the message signal M of t is denoted by P, then the signal to noise ratio at the output of the quantizer is equal to 3B over M square M max multiplied by 2 to power 2R. This is nothing but the power P over the variance of the noise. You end up getting this expression. So as you can see, the most important thing to understand the meaning of the variables and to understand the basics of communication, that signal to noise ratio equal the power of the transmitted message over the power of the noise. The power of the noise is the variance. The power of the message, whatever it is, it's P. And the variance I can calculate it from the PDF, and I just, instead of delta, I just replace delta by its actual value, which is 2m max over number of levels, L. And you get that. Is that difficult? Is that clear? Note that the signal to noise ratio at the output of the quantizer can be increased by increasing the number of bits or number of levels. So from that relationship, if I say true or false, as we increase the number of quantization level, the noise increases. True or false? As we increase the number of quantization level, the quantization noise increases. It's false. As you increase the number of quantization level, what happens to delta? Small. Since delta is small, then the probability to make errors become smaller. Signal to noise ratio is equal to, now this is true if I said signal to noise ratio. Signal to noise ratio increases as number of level increases. That's true because the error reduces. Or instead of number of level, I can say this. The signal to noise ratio decreases as the number of digits representing each level decreases. That's true. When the number of digits representing each level decreases means you have lower number of levels. And due to lower number of levels, you have large delta. If you have large delta, you have too much noise and the signal to noise ratio will be bad. See, this is physics. This is conception, intuition, understanding from the equation, relating your sense with the equation and make sure that the theory verifies your understanding. We can ask many questions about this, so you need to be ready and careful and understand this very well. So standard number of bits for audio, analog to digital. Standard audio, analog to digital converters uses 8 bits. This is actually in our phones sometimes, 8 bits. How many levels if we have 8 bits? 2 to the power 8. 256 levels. So this is just to make sure that you have high quality audio. Whereas in PC, when you have sound card, the sound card inside your PC has 16. 2 to the power 16. So you have too many levels. That's why the noise is almost ignorant. It's almost null. That's why you hear so good quality sound voice. Yes? The quality of your sound card is really very good, of your computer especially. But we can never compete with analog. For example, let me give you an example. When you hear someone like playing on the guitar, like without recording, you just he's in front of you and playing on guitar, and just feel the quality of the sound. And now record that same thing, record it and listen to it and see the difference in the quality. You must see some difference, obviously. When you are hearing the player on the guitar like in front of you, you are not recording his sound or his performance, you hear the analog version of his sound. Yes? While when you record it, you hear the digital version of that recorded sound. Isn't it? And digital, always we have a quantization noise in digital. unless you quantize for infinity. If you quantize for infinity number of levels, this means it's no longer digital, it's analog. Yes? So this is the difference. Now, to demonstrate and check our understanding for this principle, let's give a few examples. Example number 1. A given analog to digital converter is excited by a sine wave whose peak amplitude is AM. Determine the signal to noise ratio in dB if 5 bits are used in the quantizer. Repeat the problem if 8 bits are used. So the question is asking about signal to noise ratio. I must understand this, what the question is asking about. And to know the signal to noise ratio, I need to know the power of the signal over the quantization noise variance, which is this. You can write to me like this. Since this is sine wave whose peak amplitude is AM, then the power, what's the power? AM square over 2. Yes? I finished the power of the signal. Sigma square, what's sigma square? We found that it's delta over 12. Delta square over 12. What's delta? Can I come here on a side and you say that delta is equal to M max minus M min over L. What's M max? AM, because it's sinusoidal with mean 0. AM minus AM becomes 2AM over number of levels. He's not giving me the number of levels, the question giving the number of bits representing each level. How many levels we have? 2 to the power 5. 2 to the power 5, which is 32. Now you calculated delta. 2 over this, you have AM over 16. Sorry. AM over 16. This is what? Delta. You just substitute delta here and square it and divide it by 12. Since you squared it, you will have AM square here. AM square with AM square in the top goes, then you end up having only numbers. You calculate these numbers, you get the result. Let's see the answer. This is how the question is solved. I just explained in the previous slide the principle of it, which is here. This is I explained it step by step, how to calculate it and how to relate the amplitude of the signal to the signal to noise ratio and finding the variance, how to relate the variance to delta, how to find delta from the number of bits. If you understand the relationship between all these variables, then it becomes easy. Yes? Yes, it's not difficult. And then here the solution I wrote in the slides, it's almost the same. You have B here, I calculated B here, I substituted A square M over 2, and then L I represented it by 2 to the power 2, by 2 to the power R actually, but since we have delta and we reduce the variables, then the final value is signal to noise ratio is a function of R. What does this mean? The signal to noise ratio is a function of R. This shows the direct relationship between R, the number of bits, and signal to noise ratio. The relationship between them is proportional. Increase R, signal to noise ratio increases. Decrease R, signal to noise ratio decreases. And that's the thing. Okay, now this is the signal to noise ratio in linear form. But I asked in dB. To calculate the signal to noise ratio in dB, you just need to take 10 log signal to noise ratio. After you calculate this, you will end up having this value is exactly equal to this value. But this is in linear form, that's in dB form. Because the question is asking about what in dB? The signal to noise ratio, the signal to in dB. Yes, this is, I'm saying the signal to noise ratio in dB. So you must convert that linear to dB, otherwise you didn't answer correctly. If it was multiple choice like some of the exams, like in the final, and I put the answer in dB and you found the answer to be, for example, 10, and that 10 was linear, and I put 10 there in the answers. Once you find your answer among the choices, you just circle around it while you didn't convert it to dB. So be careful about this. While I'm putting questions, I pretend I am a student and solve the question, and whatever possible answers I might get and put them in the answers. So you need to be careful and cautious. Now let's see, this is then the signal to noise ratio in dB, and now you tell me for R equal to 5, the signal to noise ratio is equal to, when you put 5 here, 5 multiplied by 6, 30, plus 1.8, 31.8. This is the signal to noise ratio in dB. For R equal 8, signal to noise ratio equal this. You just multiplied 8 by 6, 42, 48, plus 1.5, 1.8. You get the result. Is that clear? Is it difficult? So far, so good. We understand everything. We don't really need to. I mean, now if you attend the lecture and you understand this and you offer the exam, you must be able to solve any question like this. I might change the number, I might change the structure of the question, go reverse, go forward. No matter what I do, since you understand this fully and you understand its meaning, this is the most important thing, then it's fine, it's okay. So now let's go a little bit harder. Now we go to example 2. In example 2, we have an analog waveform with a maximum frequency FM equal 3 kilohertz. Looks like this is voice. Yes. And we want to transmit this using M-array pulse amplitude modulation. Everybody remembers M-array pulse amplitude modulation. What's M-array pulse amplitude modulation? Can everybody remember with me? We said if we have 0, 0, then we have this level of power. We have a pulse of this level. If we have 0, 1, we have a little bit higher amplitude. If we have 1, 0, a little bit higher. Yes, if we have 1, 1, it's even higher. Yes, this is, we call it pulse amplitude modulation. Map the bits to different group of bits. We map them to different amplitude levels. This is your modulation rule. And this is what do we call this? This is 4 BAM, 4 pulse amplitude modulation. Why do we call it 4? Because we have 4 different possible amplitude values. Where the number of here in this question, I'm saying that this M is equal to 16, or let's say L. L, we don't want to call it. I'm defining it here in the question as L. It's 16, has 16 value. The quantization distortion is specified not to exceed plus minus 1%. This is what? The quantization distortion. What's the quantization distortion?
Error.
The error. And what would be the maximum error you can make in quantization? Delta over 2. Yes? Delta over 2 is the maximum possible error you can make because your quantization error is bounded between minus delta over 2 and delta over 2. It can take any value between this. What would be the maximum value when Q is in between exactly? Between minus delta over 2 and delta over 2, then you will make the maximum error here. So what does this mean? This means, this is how you need to understand the words and transform them into equations that can be solvable. So this means that the quantization distortion, delta over 2, must not exceed this. Is that true? This is plus minus, and this is also plus minus. They go with each other. We don't care about them. This is the formula I get from this sentence. Is that clear? Anybody has any objection about that? Everybody comprehending this and understanding why and how we interpreted the sentence? We said the maximum quantization error, the distortion should not exceed this value. Not exceed this value, what's the maximum distortion I can get? Delta over 2. Delta over 2 must be less than or equal this. Then from this equation, you will get the value of delta. Yes? You get the value of delta to be 2 multiplied by this becomes delta almost equal to 0.02. Is that right? Yes? What's delta now? Delta is M max minus M min over L. Over number of... now don't confuse L. Here L is for BAM. We will call the number of levels here, there, K or something else. Or we change this. We put this K or M, and here we keep it, the number of levels for the quantization, we keep them L. So here delta is equal to B analog waveform. Is he saying that we have sinusoidal signal? Then you cannot say AM. There is no AM. You need to say that M max minus M min over number of levels. We said, let's call it, where is it? Now don't confuse this, it's not 16, this is for modulation. We are in the quantization. Modulation comes after quantization. That's the mistake that everybody makes. Don't do this. This we said the number of pulse amplitude modulation levels. This, I'm talking about this. This is different than that. Here, I don't know what's that. It's unknown till now. I need to find it, figure out. But from here, M max, M min over number of values, whatever that, what we found it to be, delta in the previous example. We found it in terms of R. Yes? So here delta over 2 is equal to the maximum quantization noise is equal to 0.01 of the peak to peak of the signal that you are transmitting. Yes, and we know that delta is M max minus M min, which is M peak to peak over 2 to the power R, the number of levels of the quantization levels. M peak to peak with M peak to peak, you can eliminate them. Then you end up having an equation of one variable, which is R, and it's very easy to find this. In this case, R, when you put R, the main parameter in one side, you end up having R is equal to log 2 1 over 2 multiplied by 0.01. After you calculate this value, you will find that this is equal to 5.6 bits. And since we don't have 5 point something bits, we always have integer number of values of the bits. So we approximate it to 6. So from here, we find out that the number of quantization level is equal to 2 to the power 6, because the number of bits representing each level 6. This is very critical. Did you understand how we came here and how we linked that? I said the maximum quantization distortion should not exceed 0.01 from the peak to peak of the signal. You write delta over 2, which is the maximum distortion, less than or equal 0.01 M peak to peak. And delta, I know delta is equal M peak to peak over 2 to the power R. M peak to peak with M peak to peak, they cancel with each other. You don't need to ask me in the exam that you didn't give me the maximum value of the signal, the minimum value of the signal. You must be able to know that these can cancel with each other. I don't need it. And even if I give it to you, you must not use it, because it will complicate your solution. That's the trick here, how to cancel M peak to peak, how to find the solution without knowing the amplitude of your message signal. So after that, you end up having an equation of R only. All what you need is to put R in one side and the other variables and the other numbers in the other side, and find what that value is. Is that difficult? After we found R, the question says, this is the question, we explained the question, yes? And here, these are the points that you need to answer. The first one, what's the minimum number of bits per sample or bits per PCM that should be used in digitizing the analog waveform? From that condition that was given in the question, delta over 2 less than 0.01 M peak to peak, we were able to find that R is equal to 6. We finished first part. Now the second part, what's the minimum required sampling rate? What's sampling rate? And what's the resulting bit transmission rate? Minimum required sampling rate, how do you find it? Yes? If I give you a signal of maximum value FM, what's the minimum sampling rate? 2 times FM, 2 times the message. And what's FM? 3 kilohertz. 3 kilohertz means 3000 hertz. Multiplied by 2, you get 6000 samples per second. Now find the bit transmission. We found the sampling rate, now find the bit rate. The bit rate, you just multiply the sampling rate with R, where R is the number of bits that represent each sample. Yes? You have, let's say, 6,000 samples. Each sample requires 6 bits. 6,000 multiplied by 6 you get the value of the transmission bit rate, which is 36 kilobit per second. Come on. After that, the question is asking what's the minimum required sampling rate? We found it. What's the required bit transmission rate? Now, this is the tricky question. What's the PAM pulse or symbol transmission rate? What does this mean? What's the baud rate? What's the simple transmission rate? This is after modulation. All the ones we calculated up until now, they were before modulation. Now, after modulation, what happens? Before modulation, you have sequence of zeros and one, isn't it? PCM sequence. We converted the samples into bits, and we found the bit transmission rate. Each sample has 6 bits. 6,000 samples multiplied by 6. We found that the transmission rate is the bit transmission rate 36 kilobit per second. Now I have sequence of bits, zeros and one. I want to modulate it using pulse amplitude modulation. What do? I map each two, since I have 16 levels of pulse amplitude modulation, how many bits for each level? 2 to the power how much equals 16? 4. Isn't it? Then I take 4 bits by 4 and map them to one amplitude level. Then what would be the rate? The rate takes each 4 bits, convert them to one symbol. What would be the symbol rate? Divide the number by 4. Yes? I said I obtained the sequence of zeros and ones, which represent the analog signal. But then I want to modulate it. I want to transmit it over a channel. I have 16 levels for the pulse amplitude modulator. If I have 16 levels, this means that each level requires 4 bits. You can encode 4 bits into each level. Then I'm asking if you have bit rate equal to 36K. 36K, this is the bit rate. What would be the symbol rate or baud rate after modulation? Just divide this by 4, because 4 is the number of bits required to represent each modulation level. What's the result? 9K. This is the symbol rate. Now, last question. If the transmission bandwidth equals 12 kilohertz, determine the bandwidth efficiency. The bandwidth efficiency is bit per hertz. If you have the bit rate, your bit rate is 36, and you have 12 kilohertz, each hertz, how many bits will it carry? 3. 12 multiplied by 3 equals 36. Is that clear? The bandwidth efficiency is defined as the data throughput per hertz, which is bit rate multiplied by the channel or divided by the channel bandwidth. The bit rate, we found it to be this value divided by the bandwidth of the channel. Then this becomes 3 bits per second per hertz. Is that true? Is that clear? This is very comprehensive example, and the most tricky part of this example is the first thing when we calculated the number of required quantization bits by understanding the relationship between quantization, noise, delta, and the condition 0.01 peak to peak. Then the second tricky part of this question is how to differentiate between the number of levels that represent quantization and the number of levels that represent modulation. You must not confuse yourself between them. That's different than that. This one for quantization, this one for modulation. Let's call from now on the one for quantization L and the one for modulation M. You have 16 pulse amplitude modulation means M equals 16. You have 64 quantizer means L equals 64. And the number of bits related to number of quantization level, let's call it R, and the one related to modulation K. K is related to M, R is related to L. We will solve more questions, hopefully, and you need to practice and understand this at home because it's very important, very critical question. It teaches you many concepts and links modulation with quantization and sampling and asks you about some of the key concepts. So then here we stop and we continue next lecture.